I request you to continue, please. Thank you, sir.
Yes. Yeah. So first, perhaps we say about the switch tomorrow. So tomorrow we will first have the tutorial, derivation of the Black-Scholes formula, and then we will have the lecture. Or
Yes,
did
sir.
you
Yes, sir.
already start?
That I will inform to the participants. No problem.
Okay.
You please,
Okay.
yeah, you please
Yeah.
go ahead with
Yeah.
that plan.
Yeah.
Yeah. Thank you.
Okay. So as we have seen, most techniques which we need in mathematical finance are based on stochastic calculus. No? And the fundamental theorem in stochastic calculus, no, is what's called the E2 formula. No? And so I will now derive the E2 formula, no? And as a byproduct, we also will define the stochastic integration. There's one way to do this in a kind of an elementary way that's called the elementary pathwise stochastic integration. It goes back to Calcul stochastics on probability by the scholar Hans Vollmer, who more or less at this time developed this for educational or pedagogical purposes. But nowadays, actually, also an entire branch, let's say, not outside probability, but where probability as techniques from probability theory applied in analysis. That's kind of the rough path theory and everything where you have a pathwise integration, but where the integrator and the integrand are not of finite variation. So you don't have Lebesgue-Stieltjes theory, but you have different types of integral, which somehow depends on, let's say the fine properties of the functions we consider. So, but as I said, so this is the first instance, or not the first instance, I don't know how there also earlier in the last century, like in the 30s, there was what's called Young integrals. There are integrals of Hölder continuous function, which might not have finite variation. Okay, what we need for this one, that somehow each path of the Brownian motion has this property that the squared increases. If you get finer and finer, that's a picture I draw in the last lecture, will tend to t. So here you see that's kind of what you do in statistics and stochastics. So you do it for each fixed t, but finally you can do it, that with probability 1, this is more or less uniform in t. No, it's just a different statement here. P almost surely for each t, P almost surely this converges for each t, because everything is assumed to be continuous. So this means we want now to consider, let's say, functions, which have the same property. Meaning now that we have a function of t, that's why we denote it now like this one, not as a time index, but just a different notation, but let's say that's really a function of positive real numbers. This means it's not random, we just take one of these functions, which might come from a Brownian path or from your asset value or whatever. A continuous real-valued functions, defined on t positive, non-negative real number with continuous quadratic variation. This means instead of t, we take now any other bracket t. That's quadratic variation. And we assume that this is for each sequence that's the same. And the pathwise, if you do it analytically, it might be that actually for different sequences of partitions, you get a different one. If you are interested in the analytic side of this actually depends. That's an assumption which we have here, that this does not depend on our sequence Teufel. In reality, it might be, there might be examples where this gives for different sequences, like you take the dyadic one, you divide always by half, you get finer and finer. Then you get a limit. If you take another one, like 1 over n, you will get a different limit here. So that's an assumption in reality that this does not depend on this one. So this we call a sequence PMZ, the partition sequence, mesh conversion to 0. Then we have the famous Ito formula, that f of xt equals f of x0. Our f must be now in C2. And so we have that the integral from C to f prime xs dxs. Again, if xs would be a finite variation, the variation norm. Variation norm is the same with absolute value instead of squared. If this is finite, then this will disappear. So then we have the fundamental theorem of calculus. That's why you can also see so if it's less regular, then you get an additional term. You see one thing here, if the integrator is less regular, you need more regularity on the integrand. Because here we need C2. So in a classical analysis, we just need f to be in C1. Okay, this formula we want to prove. First, we have to say how this integral looks like. So we have to not defined as in the back Stieltjes or Riemannian way. Usually integrals are defined like the Riemann integral, which you learn standard integral in calculus, where you take the, how do you do a integral? You take the sums, and sum up here. Integration, Riemann integration is basically, you measure somehow the volume below the curve. There's a very specific defined, this stochastic integral. It's defined if you have a function f. This must be now in C1, because it's small f to be applied. But the definition of this integral, it's defined like a limit of a sum, as in more or less any integration approach. You take this partition, you look at the increase, but then you evaluate on the left-hand side. Always evaluate on the left-hand side. So it's important where you evaluate. Like Riemann integral tells you, okay, it doesn't matter where you evaluate, you always get the same sum. You always, if you take this one, actually take this one. Here you take this. You take this. So it's always left side. So what we have seen, so far in our let's say discrete market time, that's your investment. It's a special investment, which just in this case, it's adapted, no? And we look, that's the future one. That like when you make your decision, so this is adapted to this hedging strategy of self-financing strategies. Yeah, so this statement tells you, okay, yeah, if we define it like this formula holds. For a function x, which does not fulfill the classical assumption of the assumption of classical analysis, Riemann integral, the Beck integral, whatever type of integral you have learned in calculus, or analysis, or differential equation, or whatever. Or what which I call classical analysis. This means, and so the second integral, of course, because xs is increasing, it adds positive numbers, and it then adds more. S to x, s is increasing, or non-decreasing at least. It's a distribution function and positive. So this means this can be defined. So this, you see, that's a classical definition. Here psi I must just be somewhere in the interval, and classical integration allows you to take any psi I in the interval ti to ti plus 1. So that's just a difference. You take a specific evaluation point. And in the Beck-Stieltjes integration, this doesn't depend on the, by definition, it doesn't depend on the PM set and doesn't depend on the vector xi. It looks a little bit strange, but that's the case. In stochastic integration, you just take a specific point where you evaluate, and that's why this specific, is what's called the non-anticipative stochastic integral. That's what we call Ito integral. It's important in mathematical finance. Actually, there are other integrals, which we will see later, where you take a different evaluation point. You can choose another one in the interval ti to ti plus 1, and each time you get a different integral, different value of the integral. Okay, but let's look a little bit at Brownian motion. This we prove usually in probability 3 or in a lecture before has a quadratic variation t. This comes from the effect, put it like, because the increases itself that's ti plus 1 minus ti. So this comes from the fact that the second moment actually, you first show L2 convergence and then you show that. So in how you prove this, it comes from L2 convergence. Because let's see, the second moment is actually time. So that's not a surprise. Put it like this, it comes back. If you know it. Okay. If xt is a Brownian motion. Okay, now we look at this different, we call it also p variation sometimes. So absolute variation is the one. Here you see, okay, what you can do. You see, you can just take a fixed number of points. You take one of your partitions, so fixed n. Then you can take out the maximum of the increase, and you are left with the variation norm. Well, that's now the discrete version of this. And then because on a fixed interval that absolutely continuous, this converges to 0. Yeah, and if this is finite, then quadratic variation converges to 0. And you can do it with any alpha plus beta. You know, when one is fine, this always, if this explodes, if this is finite, if quadratic variation is finite, then you get a finite, a non-zero finite value here. If quadratic variation is positive but finite, then the absolute variation must be infinity. This is between 0 and infinity. It's finite but positive. Then you had infinite absolute variation. On the other hand, if you have finite variation, this means the limit of this one as the mesh tends to 0, tends to a number, then this one has to become 0. That's what I said. To have always 1, if you take alpha plus beta, you see the relation between alpha and beta. Alpha and beta equals 1 at 1. But the same arguments, of course, works for other alpha and betas. And that's why, meanwhile, you have this 1p1 plus b1 plus p smaller than 1. That's kind of, sometimes it's called also roughness. Rough path. We have a p equals 1 rough. So Brownian motion is p equals 1 rough. No, it's not called rough. But as I said, so that's a quite important development in analysis, in outside probability theory, but also in probability theory, because you have now rough markets, rough volatility, and stuff like this. So it's basically goes down to simple insights like this. Okay. Because this the limit, the quadratic variation is sorry, because the quadratic variation is a it's a monotone, non-decreasing continuous function. It is a distribution function of a continuous measure. Then basically the convergence of these discrete quadratic increases to the quadratic variation is what's called weak convergence. That's weak convergence is in this case equivalent that it converges for each t because there's no jump in t. That's kind of measure theory for real-valued measure theory. For measures on zero on the real numbers. So this means the left-hand side, this one is of course this measure mu n. It's written here. So mu on the interval ct, mu next n. On the interval 0 to t is exactly the quadratic variation. The discrete approximation to the quadratic variation. This means, why do we want to have this? Because then we can say, okay, because it's weak approximation, instead of taking the indicator function, we can take any bounded function here. And that's the next lemma. So that's the left-hand side is integral g mu n. We had point masses only on Ti, namely point mass, a quadratic increase on the next time interval. This converges to this one. We have more numbers which converge and not only the quadratic variation. That's like the definition of V convergence, and just means that every integral with respect to the bounded continuous function converges. Mu n to mu weakly. This is a case because the distribution functions on E, the distribution function that's equivalent, we have shown weakly up. So this means in this special case where mu is continuous, we assume that the quadratic variation is continuous. We have that mu n 0t converges to mu n to mu 0t. Is equivalent that it converges weakly, and this is equivalent that all integrals with respect to continuous bounded functions also converge. This we need in the proof of the Ito formula, which we will do here in detail because it's a basic step which is important. Okay, how do we do the proof? That's again just a statement, what we want to prove. Let's go here and do that again. Okay, that's our Ito formula, where this specific integral is defined at this non-anticipative limit, or left-hand side limit, however, left-hand side Riemann integral, however you want to call it. We do Taylor formula. So we know that because f is twice continuously differentiable, we can write the increase over from xti to xti plus 1. It's the derivative. That's Taylor's formula applied on the two numbers a, b, and a. B minus a, second derivative, plus a remainder term, which is in some sense we first now consider the remainder term, and we will see that the remainder term is bounded. Now you can look it up in the textbook on analysis. That the remainder term can be bounded if your xs prime minus xs is close enough, because x is continuous. So this can be achieved by having s prime and s close enough. So x of s is continuous. F double prime is also continuous. We just have to choose our t1 small enough so that the ti plus 1 minus ti close enough, such that x ti plus 1 minus xt is still as close as we like. And so we can do this upper bound on the remainder. You see here already appears the quadratic variation, which is finite. And this one, of course, because it's continuous, again, this will tend to 0. So this means the remainder term, if we sum it, we can take out this one, which we have to assume to be smaller than epsilon. even if we put in here the xt plus minus 1. Huh? So this converges to something finite, so this converges to 0. So the remainder term disappears. That's very good. Okay, there's a telescoping sum. No? No? We have only largest and smallest t, and so this will converge because of everything is continuous. So it converges to f of xt minus f of x0. Okay, on the other hand, that's what we have, this lemma on the V convergence. So this integral converges, this term converges. So that's the 0 term in the Taylor expansion. This one is the second term in the Taylor expansion. This converges to the classical integral because this is, as we have seen, comes from a measure. It's a distribution function, however you want to put it. Okay, so everything converges, so that's good. This means also the first order term in the Taylor expansion, if we sum it, should converge. So this converges to 0, this converges, this one converges, the sum over this converges to 0. This one converges, you sum of this one, now we sum it again. Sum. This converges to f prime d quadratic variation. This converges to 0, this converges to f of xt minus f of x0. So this must also converge, and just we call it. Everything converge. Hence also this limit must converge. This means if we have a path continuous with positive finite quadratic variation, then we take a sequence of partitions which size tends to 0, and we assume that the limit will be the same for everything, then we get this E2 formula. This is elementary. It's just applying Taylor formula. There's no stochastics here, no probability. So again here, if you write it formally as differentials, dfx equals f prime of x dx plus 1/2 f double prime x dx. That's then called E2 calculus. You can formalize it. But these differentials, of course, does not exist. F of x is not a function. So x itself is also a function. It's not like you have two variables like x and y. So you have two differentials. You have just one variable x, which has two kinds of differentials, if you like. Because this dx doesn't exist. It's not differentiable. Now, as an example here, if you want to write down differential equations, for example, if you have the sequence of differential equations, the simplest one, like the one solved by monomials, like x of n, they can be defined in classical analysis. Fn prime of x equals n times f n minus, no, it's not the power, that's an index, it's probably badly written. But at the end, it's of course the power, yeah? The power functions. So the polynomials are then sums of this. Yeah? You can write down the differential equations solved by the polynomials, which, yeah, but here this means polynomials described in terms of differential equations are like this. Yeah? So sum of this, because everything is linear, yeah, so you know how to solve, to define polynomials in terms of the differential equations. So polynomials is a building basic block in classical analysis. So, and we now look similar thing in stochastic analysis. We want to find functions, yeah, such that dxtn equals nxtn dxt. Yeah? Unfortunately, that's not just a polynomial. It does not taking power in. Yeah, because by E2 formula, yeah, if f in our E2 formula, if we take f index n of x to be x to the power n, yeah, we get this one from the E2 formula. No, and it does not satisfy the same differential equation. So they are quite involved. The analog on the integral for Brownian motions are the functions. If x is a Brownian motion, this depends on the x. We have here. Now, on the other hand, if you don't like numerical assessment, you can just define your stochastic integral like this. Now you take f, a C1 function, and for a C1 function, you can define the stochastic integral by E2 formula, taking the functions capital F, which is the integral, the indefinite integral, and f of x you can define like this. And you don't have to do. Of course, this one you need to know. This classical integral, put it like this, so the correction term, if you like, or stochastic term. It's not. There's no stochastic here. It's a quadratic variation. Okay, and that's the main feature of the specific type of doing the integration. It's non-anticipative. It does not look into the future. That's why you use it for finance. It's related to hedge strategies. And like in stochastic analysis, or like in other applications, there are other integrals. You just take, like it's a 1/2, you take the midpoint, or if alpha equals 1, alpha equals 1, you take the right-hand point. Then you call it backward integral, because then you have f of xt plus 1. You always take on the left-hand side. Well, and like in physics, this plays an important role, like time reversal and stuff like this. So this appears in other applications of stochastic calculus, where you look at time reversal. And you have the formally, so this means the backward integral is non-anticipative after time reversal. And the one alpha equals 1/2, that gets its own name, Stratonovich integral. Because for the Stratonovich integral, if you rewrite we define now with the circle here, we define to be the Stratonovich integral?
Excuse me, sir.
Yeah.
Sir, one general question.
Yes, please.
Sir, as you defined earlier, H and X, Hermite
Excuse me.
polynomial. H and X. So is it Roderick's formula for Hermite polynomial?
Yeah.
Or what?
Yeah.
Yes, sir.
Yeah.
So is it Roderick's formula for Hermite polynomial or a simple Hermite polynomial?
I didn't understand. I just know this, that it's called Hermite polynomials. But you have a second name for this, another? Which formula?
Roderick's formula, Roderick's.
Roderick's formula, I don't know. No, that's just the definition of Hermite polynomials I know. Huh?
So we write a Roderick's formula for Hermite polynomial like h n x equal to minus 1 to the power n into e to the power x square into nth derivative of e to the power minus x square.
Yeah, that's the definition of a Hermite polynomial I know. Of course, you can calculate if you like this, but this doesn't look nice, yeah, because it's a.
Okay,
Yeah,
sir.
Yeah. So I don't know. Of course, then you have a sum here, yeah, which is x squared and so on. Yeah? So actually, I don't know the explicit formula. Put it like this. Yeah? That's the easy way to write it. Yeah? It's just to tell you, even the simplest equation, yeah, is much more involved, and it depends on that x is a Brownian motion. Yeah. So, but that's a. I still didn't. Perhaps you can write it in the comments. The formula you mean, just the name, because I didn't get the name. Huh? Actually, this will never appear in stochastic in mathematical finance. It appears in some other applications of stochastic analysis, like in non-anticipative calculus and so on. So there are some, because these Hermite functions build somehow a basis of continuous functions and so on. So it's used somewhere else in like the polynomials build a basis. Yeah? These also build a basis under, and it's more important what's called calculus on Wiener spaces, yeah? Or White-Noid analysis. Like, or Malia-Wern calculus. So that's kind of put like even more functional analytic. Huh? So have you written what's the name of the formula, Mr. Kumar?
Okay, sir, I am writing.
Yeah. Okay. Okay, the advantage of Stratanovich formula is that the E2 formula rewritten with the Stratanovich is actually fundamental. It looks like the fundamental theorem of calculus. So this means every, let's say, analytic area where you need a lot of differentials, like differential geometry, what's called the stochastic differential geometry. That's actually formulated in terms of the Stratonovich integral. Because here you see, you can just take, write it like this. Sometimes people write it like this. And think these delta, that's the Stratonovich differential. Then you can put it in, and then you have the same rules as in classical differential geometry if you consider stochastic differential geometry. This is like Brownian motions on manifolds. So it's an area of stochastic analysis. But for us, just interesting in mathematical finance, the main advantage of this type of integral is the E2 integral. And as I said, it's very important. Rodriguez, okay. Yeah. So the main, but I don't know this formula. And the main application is that if you start with a martingale, you get a martingale. And of course, I mentioned this, of course, you always have to say local martingale, whereas in a real example, you always have to prove that your local martingale becomes martingales. Okay. I come back shortly. I have to re-enter again.
Okay, sir.
Yes, I just have to reconnect my other device again. It was.
Okay, sir.
Just a second. I have to reconnect with the other device. Yeah. Sorry, my iPad, or not an iPad, my other device. I probably need to restart this. So sorry, I have to restart the iPad. And it's still running Teams. Join now. I share again. Okay, the first step from after the simple E2 formula, we will look at the d-dimensional E2 formula because, of course, we have markets where you have more than one asset. So this means we look now at d-valued functions of t. Put it like this. So t to xti is continuous, where I runs from 1 to d, and we take a twice differentiable function on rd. And so we get this formula in the same way as we get the one-dimensional by looking at these Taylor expansion for functions, for vector-valued functions. So you get the first term, where this is defined again in terms of, I mean, in reality, you have to prove something that, of course, this one is, you only know the convergence of this entire bit. You have to identify this to be of this form, that it's the same as a single subs. Okay, but basically the formula looks the same. And it's always first derivative integrated with a process. That's stochastic integral minus 1/2 second derivatives integrated with a covariation, which I explained to you before. It's the sum of the product of the increases. As I told you, this bracket, if you have 2 entries, it's like a bilinear form, and it can be achieved by polarization. So for each single, it's the covariation can also be written 1/2 times this one. No, that's like a property of bilinear forms that you always have. And so the proof works then as in the one-dimensional case. Okay, we now need a little bit more properties of martingales. So martingales actually always have nice path properties. They are what's called Cadillac. So because you always ask about jump processes. So jump processes are modeled on what's called Cadillac spaces. So your jumps always have to look like this. Here you have your hole, and then you jump to this point. So they're right continuous. The jump is so x t plus equals, if you come from above, it's the same as xt. And martingales always can be embedded in this space of Cadillac. This comes from the French. It means it's right continuous. And limits are with left limits. There is a limit, it doesn't oscillate. But if there is a jump, the left limit, we just construct it like this, the left limit, it's it jumps shortly before the time, not at the time. At the time, it's already, at time t, it's already on the place where it jumps to. You have to decide somewhere. Of course, you have also other versions of this. You can also make martingales the other way around. So basic property is that they behave nice. They cannot oscillate too much, martingales. And this follows what's called the martingale convergence theory. Martingales also converge in many cases. And for a fixed time, of course, they converge. This is a famous martingale convergence theorem. You can imagine it's somehow similar like the law of large numbers. Because you have also a martingale itself is a sum of the martingale increments, and the martingale increments, they have zero mean. It looks a little bit like a sum of IID. But the martingale convergence theorem is a very important result for martingale theory. And so but in mathematical finance, we just use it for the property that they have. Huh? For us, it's more important. I already mentioned this in the case of discrete martingales, that if you have a stopping time, then the stopped martingale is again a martingale. Huh? So the stopped martingale is you stop at time t, stop at time t. This means you have a martingale here. It's really slow. You just make it constant from here. That's the stop path. It just takes the just takes the value, the value at t, and then it goes further. Yeah. So this means if small t is larger than t of omega, you always take the value of t of omega. Yeah? You also see here it can be bounded. It's again, it cannot fluctuate too much. So the supremum can be bounded by the last value. Hmm? And so for all the convergences, we have like this V convergence of random walks to Brownian motion, which we don't prove here. But basically, it also comes from the convergence of martingales. If you have a sequence of martingales, like the random walk or part of the random walk, then you can approximate this one. Yeah? Actually, this we all need. This, for example, this proposition we need for the general construction of the stochastic integral, which will come shortly. Skip the proof here. Okay, after we have defined the elementary formal and the elementary stochastic integral, we want now to define for any martingale, like the Brownian motion or like a diffusion processes or whatever, we want to define the stochastic integral, but not only for functions of the integrator, but for general random functions or processes AS. So we now are, so before we just have what we have done, just to get the idea, we could define stochastic integral of this type. And so the next step here, we want to define it, general martingale, and which type of stochastic processes can we integrate here. Of course, what we also do here, we take step functions. Our ASN will be step functions. So we have our filtration, and we still have to do it because we apply it in mathematical finance later in a non-anticipative way. This means our hedging strategy, in mathematical finance, you also call it simple hedging strategy, is just a step function. Even it's in continuous time, you stay constant. You invest at time ti, you invest this amount in the stock, if in the stock M, if you like, and AI must be FTI measurable. Here you see what was done called predictable. We take the open interval here, and this must be FTI measurable. So now you see that's how. That's a left continuous process. And then we define this one. Now, if we have this simple hedging strategy, we get a process, which is a value process of the simple hedging strategy, and we get a martingale again. Okay. Okay, again, what we don't do in detail is that we take local martingales instead of martingales. I defined it already what this means. So now we come to this compensator. So that's the other way of getting the quadratic variation. So we haven't done it here because I didn't tell you so much about martingale theory in discrete time. But in discrete time, for every submartingale, submartingale what is a submartingale? This means expectation x if it's given fk minus 1 is larger than xk minus 1. So it's increasing. On average, it's increasing. So what I mentioned before, it's important to compensate this increase by Vk. So this means xk by simple calculations of conditional expectations, xk Vk is a martingale. So that's what's called the compensator. So it's an increasing. In order to be fair, again, put it like this in financial terms, because we know this fair games or fair markets or martingale probabilities are important, we have to compensate this. And we can do it elementary in discrete time and space. Okay, because we want to get the quadratic variation of a martingale, we take the martingale squared, so we get a submartingale, and then we call this one in discrete time. This is mk, meaning that mk squared minus quadratic variation is a martingale. This means the second moment of the martingale is the first moment of the quadratic variation. Now, if you think in terms like in classical risk theory, risk is volatilities, variances, and so on. All the uncertainty in your asset price, which in economic sense is related to intuitively the volatility, which is related to the second moment, you get from the quadratic variation. Because expectation of mk squared equals the expectation of the quadratic variation. That's why quadratic variation is so important in mathematical finance. And here you see that if you do the same along Tn, tau n, that's a sequence of partition which depends to 0. You define at each partition, you define the increase of the squares. That's like the pathwise definition we had before. That's now here a stochastic process. So But it's interesting to see what you see here already. Yeah? If you take the binomial formula, actually, yeah, you see that it's the same as this one. Yeah? And here you see this one is actually ms d ms in the limit. Yeah? Okay, but that's good, yeah, because it's M is a martingale, this one is a martingale. And you see that MT square, let's assume this limit exists, and we call it M, bracket. That's a martingale, and especially we know how the martingale looks like. Huh? Okay, this simple, let's say, based on binomial formula, yeah, already shows that first we have a compensator also in continuous time. It's the limit of this naive or discrete time compensator. No? And we know how the martingale looks like. We just claimed that MT square minus MT is a martingale, but actually we know how the martingale looks like. It's a 2 times the martingale integrated with itself. No, and how you prove it? I mean, this is now done in probability theory. We first prove that these, what we have defined for fixed n is a Cauchy sequence. And so it's itself a martingale, and it's a L2 convergence. For each n, we have a martingale. So the limiting process is also a martingale. No? That's everything is in L2. For fixed t, that's in L2. Huh? And because it's continuous, it's enough to do it for fixed t. Huh? So here we show, I mean, the assertion was for fixed t. That's now a typical probability statement. We first show something for a fixed t. Yeah. And now we know for fixed t, the probability is 1 that this converges. Because everything is continuous, we just have to do it for all, let's say, rational t's, which is again a 1 set. Because it's continuous, it converges as path. On space of continuous path, we have this convergence, almost sure convergence. Okay, but you can get it easier if you like. You just apply E2 formula to f of x equals x squared. Again, I mean, of course, that's not in CB square because it's not bounded, this function. Yeah? But let's assume we could apply E2 formula also for x squared. Then we would say f of mt minus f of m0 equals that's E2 formula. I mean, if you want to do mathematical finance, you have to know Ito formula by heart. No? Okay, this one is 2, second derivative of x squared. This one is 2m. Yes. Here you see empty squared minus m0 squared equals integral 0 t 2 ms dms plus so here m t. This cancels. Huh? Okay. Yeah. Though it's all martingale theory, it's good to get a martingale because martingale gives you martingale measures, which gives you prices. And then we define here the same as in the pathwise by polarization. We also define this one. No? No, that's, I mean, either you just extend this elementary Ito formula to processes, so that somehow step by step we do it here. So we get also for processes, we get this one. No? We have to work on the quadratic variation more. No? So to get these limits and so on, we have to bound it. No? So we have like the Cauchy-Schwarz inequality, which just comes from the effect that this is a bilinear form. So it's bilinear in M and bilinear in, so it's a bilinear form M and N and bilinear in H and G. So you can easily prove similar to Cauchy-Schwarz. That's a pathwise property. You can prove this one. And it's not directly Cauchy-Schwarz, but it's the same proof as you prove Cauchy-Schwarz for scalar products. And then you integrate this one, and then then the application of Cauchy-Schwarz in L2. Everything is very similar to classical analysis on Hilbert spaces. Where you have Cauchy-Schwarz as well. Okay. And as you can imagine, you just do it for step functions, and then you can do it for general integrators by taking limit. That's what's called the another if you sometimes work in probability theory, that's some measure theoretic induction. That you prove something for step functions, and because step functions, all measurable functions are limits, monotone limits of step functions, you can prove it for all functions in the specific measure space and so of the specific type. Okay. And that's actually the proof is here based on, but this you can look up in any textbook. Okay, now we construct this. Okay, now we are ready to construct the stochastic integral in the Hilbert space of continuous martingale, which have also second moments. The space we are constructing integral. So our integrator should now be a martingale with continuous path and where the second moment is also bounded. That's because we want to apply convergencies, the convergency based on L2 convergence. Of course, there are more general approaches, or you can do it by localization, but you can extend this construction further. And the basic idea is that as I said, we define now, because they converge, All we have to know, because we have the given filtration, and the if it's an uniformly integrable martingale, it converges to a final martingale, a final random variable, and all others can be obtained by taking the limit and conditional expectation, what's called successive predictions. Of course, in this setting, it looks a little bit weird. F infinity. In our setting, actually, it's even more natural. We should adapt it to a finite time, because here we have our t is now final time of market. Let's say of market. So this means in mathematical finance, this becomes easier, because if it is a martingale on the bounded interval from 0 to capital T, all you need to know is the final random variable MT and the filtration FT. You have seen it, the value of a portfolio and the value of a derivative or whatever is always the expectation of the final payout, which we called in this context always X. All our martingales or VTs are our expectations. X, this was our derivative given FT. And if you like, you have transferred everything. Yes? Excuse me? Was it a question? Sorry, I didn't get it.
No, sorry, it's fine. It's fine.
Okay.
I think some noise also. Yeah.
Okay. Okay. So we can do stochastic. I mean, just we do stochastic integration and it's a Hilbert space with this norm and so on in order to get a easy way to do this. So it's isomorphic. So the space of our martingales is just isomorphic to the L2 space of all random variable taking the limit. If you start with a martingale and if you start with a random variable in this space, your martingale will be x, just a random variable here. You take your martingale to be the expectation of x given ft. That's the isomorphism between these two spaces. Or if you have a martingale here, you define x to be the limit. And you can reconstruct x from here. Okay. And so the norms is related to the quadratic. That's actually the most accessible, if you like, is a quadratic variation, because there is no stochastic integral yet. But we will define the. So for elementary left continuous processes, which we had done before, we define the stochastic integral by this discrete one. That's again a stepwise definition. Discrete time. And again, I say it again and again. Left-hand side. Now we define it like this, and now we approximate. So we take the closure. That's like Hilbert space theory, if you like, or we learned numerics. It's also a numerical issue here. You just take the closure of this space of elementary functions with respect to a norm, namely the norm. Which we have defined in MCS. MC quadrat. For this, we actually have to know this famous Ito isometry, meaning that's the norm of a stochastic integral. It's nothing, in this case, it's nothing else as here you take the quadratic variation of the norm, That's our Hilbert space. Yeah? Here we want to take a Cauchy sequence and takes a closure. H started in the elementary one. And we get a Cauchy sequence with respect to this norm. And this norm is actually calculated. You see it's also an L2 norm. Where you have this kernel integration. You integrate H S of omega squared. You integrate by quadratic variation, which is also, it's a measure. And here it's a kernel for each omega. This is a measure, and here you have PD omega. So we integrate from 0 to infinity, and here you integrate over omega. So this is a double integral. If you write in terms of integral, and this one is a measure on positive numbers times omega. Huh? Or vice versa. Okay. First, we have to show that for elementary functions, we have this. We have the norm of this one. So this is the isometry between a norm space of martingales and the norm on processes. And here, okay, I wrote it down here. So we are now integrating on not only on omega, but also on time. So this means we have an L2 norm in order to apply a Cauchy sequence and completeness and so on. Okay. This means the extension of the simple step functions, and it was not step function, of this elementary E2 formula tells you that for all functions which are in the closure of the elementary functions with respect to this norm, we can define the stochastic integrals because we have Cauchy sequences. Okay, that's, put it like this, that's the most largest space. We start with a simple one and we take the closure. Of course, in reality, you might want to know which type of processes are in there. You can see it. Like P. These are those processes which are left continuous and adapted, and you take this as an integrand all the time. You can take it as an integrand. So P is a subset of this closure by construction. But because it's continuous, it's also the optional ones. These are the ones which are, so let me see. So probably this becomes too detailed. Anyway, I think time is over. I mean, it was just to explain you can define stochastic integral in a kind of elementary way by Taylor's formula at the beginning, but it coincides with a more general one where you do it for any type of martingale. In this our case, not any type. We have martingales to be continuous and square integrable, and the integrand is actually any adapted process. And because if MT is continuous, you don't see the discontinuity of the integrand. So a large class of integrators and integrands associated with this. So I think I stop the lecture here. So tomorrow we will first have, based on this one, meaning based on E2 formula. I told you the only thing you have to remember is E2 formula. Because we will apply it if we derive Black-Scholes formula.
Many of them might be knowing it, sir. Many of them might be knowing it, but yes, So all the participants, you just explore, and if you don't know, and if you know, just revise it, the Ito formula. That
Yeah.
sir is telling that he'll be using it tomorrow in the Black-Scholes derivation.
Yeah, yeah. So for continuous for the deriving the PDE, we will derive the Black-Scholes PDE. We need Ito formula. Yeah?
Yes, yes.
And it's important to understand how this is connected to pricing. Okay. Thank you very much. So see you tomorrow. Yeah.
Thank you so much, sir. Thank you for your nice lecture, and I thank all the participants also for being present in the lecture. So thank you, sir. We'll meet tomorrow.